Okay, today we're going to look at the last lesson for this unit, which is on periodic trends. Periodic trends are a way of looking at the overall change in the electron configurations as it progresses on the periodic table. So we're going to look at is how we move from element to element on the periodic table. So what I mean by that is that we're going to start with hydrogen and compare it to helium. And compare hydrogen to lithium and basically compare it to all the other elements and see how things change. So what happens as I move or progress from hydrogen to helium? What happens as I move from fluorine to chlorine to bromine to iodine? We're going to look at a number of properties. So these are called trends, is what we're looking at. Trends are changes or things that happen as you move across the periodic table. So there's two types we're going to look at. One is a periodic trend. The other is known as a group trend. Okay, so group trends and periodic trends are those changes that I was just showing you. So a group trend goes up and down on the periodic table. So this would be considered a group trend. We would look at what happens with the alkali metals. So we would look at what happens to the atomic size. Does the atom get bigger or smaller as I move down? And then we're also going to look at periodic changes, which would mean going from left to right on the periodic table. So I would look at how does sodium, magnesium, aluminum, silicon, how do they change? And what I would be looking at there is I could be looking at atomic radius, or I'm going to be looking at ionization energy. So we really just introduced two types of trends in this video lesson. So periodic trends, group trends, and then we look at atomic radius and the ionization energy. Next chapter we're going to look at electronegativity, and later on we're going to add more to this as we go through the rest of the school year. All right, so let's take a look at the first one, which is atomic radius. I'm sorry, here's the two properties we're looking at. My fault. We're looking at atomic radius, which is the size of the atom, and we're looking at ionization energy. Very important that you know the definitions, know what these two terms mean, because you can't really go too far if you don't know what they mean. So this is talking about the size of the atom. That's pretty obvious, pretty straightforward. Right? Radius is the distance from the nucleus to the outermost electron, which would mean the valence electrons. Right? This would be called your valence electrons. Now there's a lot of debate about the size of these atoms, so we're not going to be looking at the actual numbers. We're going to be looking at the rounded rough numbers. But we can pretty much conclude that sodium would be a lot bigger than magnesium, and neon would be a lot smaller than sodium. Okay, then we could talk about the ions, which we already talked about in the last chapter. But for now, we're going to look at the next one, which is called ionization energy. Now this is the energy needed to take the electron out of the atom. So think about this. You got the nucleus, and you got these electrons that are in energy levels, and this electron is in the atom. What we're going to do is we're going to try to hit energy. All right, we're going to use energy to try to knock that electron away. The energy we're talking about, ionization energy, is the energy needed to make the electron escape from the atom. So basically what we would have left over afterwards is we would have just, the positive charge and the electron sitting out here all by itself. That would be ionization energy. Energy needed to remove the electron from the atom. Think about it. What's holding the electron back? It would be the pull of that nucleus, right? So if the pull of the nucleus is pulling that electron in the atom, the better it is at pulling the electron, the higher the ionization energy, right? So if the electron is being held with more energy, the ionization energy needs to go up and go up and go up depending on how it is. And this is important because if we're talking about electrons moving, that's chemistry, right? That's forming chemical bonds. We're going to talk more about bonding a little bit in the next unit. But that's the idea, is electrons moving from atoms or moving into atoms is chemical reaction. So this is a very important concept. All right, so let's take a look at atomic radius first. So the atomic size is going to change. If you think about it, if you add electrons and protons, the atom should just get bigger and bigger and bigger. So if we looked at the data, we should see that the smallest atom on the periodic table, okay, if that's the idea, we start with hydrogen, okay, which is just one proton and one electron. That should be the smallest atom. And the last element on the periodic table, the Uni-octium 118, should be the largest, right? We should see a smooth, continuous increase. But you hopefully know that according to quantum mechanics, it's not going to be the case. So we go from, when we look at our group trend, remember, this is that trend going up and down a family, okay, our group on the periodic table. What we actually find is that the atomic radius increases as we go down. Okay, which makes sense. Maybe the atom's getting bigger and bigger because more protons are new. So it seems to go with our flow there, what we're talking about. But the reason why that happens is because we're adding new energy levels. As we go down from hydrogen to lithium on the periodic table, what happens is we add another energy level. Remember, there's energy level 1, energy level 2, energy level 3, 4, 5, 6, and 7. If you look at the electron configuration for hydrogen, hydrogen is going to be 1s1. Lithium is a 2s1. Well, don't forget about the fact that lithium has helium in there, so it would be helium, and then it would be 2s1. Now, why is lithium bigger? It's not just because it has more protons and electrons. That's not just it's not as simple as that. It's because it has a higher energy level. Because that energy level for that electron is further out. So here's hydrogen, here's lithium. Lithium's bigger because it's in the second energy level, n equals 2 versus n equals 1. So because I added a new energy level, my atom is going to get larger there. Alright, so let's take a look at that again. So from top to bottom, the atom is going to get bigger and bigger and bigger. So as n increases, the number of electrons, or the energy level increases, the electron can get further away because it has more energy, and the atom's radius is going to increase. Alright, now let's take a look at the periodic trend. So that would be going from hydrogen to helium, lithium to neon. Well, if we follow what we said earlier, that if I add protons and electrons, it should get bigger and bigger. Here's where things are going to contradict. From left to right, atomic size actually decreases, actually gets smaller, so it's not going to fit what we actually think. Because as we move along here, we are staying in that same energy level. Our energy level doesn't change. So from lithium to beryllium, we're staying in the same energy level. But what's happening is we're adding more protons to the center because we're getting 3s and 4s. So now you have 5 protons, and those we do have more electrons, but those electrons are now in the same area or the same energy level. And this is where things are a little bit more confusing. You got to kind of think about this quantum mechanically. Because they're in the same energy level, they all have the same roughly the same energy. So therefore the nucleus will pull them in with a greater force, making the atom smaller and smaller and smaller. So the trend going across a period is definitely different than we see for going up and down a group. So we see a decrease in the size of the atom. Very important to know the why. So make sure you understand the why as well as being able to identify the trend. Alright, so if we look at the overall periodic table, as I said earlier, we would think that the hydrogen should be smallest and our last element should be the biggest. And it's not the case. Really, our biggest element is here, and our smallest element is up here. Right? So francium would be the biggest, while helium would be the smallest. So it's actually the opposite than what we thought. Okay, why is this? Because of energy levels, because electrons fit in energy levels. Here they're in the same energy levels, and the protons are increasing, so we get smaller and smaller. Now this is a complete over-exaggeration of the data. We see a lot of up and down in the data because it's not absolutely perfect, and we can talk about more of that as take the AP Chem class or a college level class. For right now, we're looking at the overall generalization. Okay, so as you go down, the atom gets bigger. From left to right, the atom gets smaller. All right, let's take a look at ionization energy. So this is data regarding ionization energy. Atomic number increases, and this would be the elements and their ionization energy. So we have hydrogen down here, helium up here at the top. So that would be going across a period, and then if we go down from helium to neon, we could see that this ionization energy goes down. So ionization energy goes up and it goes down. So this is our data. You notice it's not a nice straight even line. You see the zigzagging pattern because of the fact that we have quantum mechanics here. This is not just a straight linear function. Alright, so what do you need to get out of this? Alright, so from left to right on the periodic table across a period, ionization is going to increase. Okay? If we go back to this picture here, we know that if we go from left to right, the atom gets smaller. Why is the atom getting smaller? Well, because the nucleus has a better ability to pull the electrons. Since it has a better ability to pull electrons, it's going to make sense that this side of the table is better at pulling electrons than this side of the table. Hence why your nonmetals tend to gain electrons, and these are easy to remove. Those metals have electrons that are very, very easy to lose their electrons because their ionization energy is really low. So if we look at our metals down here, lithium, sodium, here's our alkaline metals. They're down at the bottom. Very, very low ionization energies. So francium being the smallest, because again it's the biggest, so therefore it's easiest to lose the electron. And I think I'm going down a family when I meant to go across a period. I'm sorry about that. I'll come back to that in a second. So lithium to neon, we see that there's a general increase in ionization energy. My fault, because we're going from lithium to neon, and we're staying within the same group or family, and therefore we are keeping the number of electrons. So from left to right, the ionization energy increases because we go from lithium to neon. We stay in the same energy level and add electrons to that same energy level. So therefore, from top, oops, my fault, wrong button. From left to right, the attraction increases because of the number of protons. So the ionization energy goes up. So it's harder to move electrons on the right side of the table. As I was saying, on the other side of the spectrum here is the group trend going down from top to bottom. Ionization energy is going to decrease. Okay, we can see that in this data here because as we go down the periodic table, lithium, sodium, potassium, rubidium, francium, we end up with a smaller ionization energy because the electrons are getting further and further away. Why? Because we now add a higher energy level and the electrons further away. So there's a new energy level added. And as that new energy level is added, the ionization energy decreases because the electron gets further and further away, and it's easier to remove that electron from the atom. Also take a look here. Helium, neon, argon, krypton, they have very, very high ionization energies, which means it's really hard to remove those electrons from those elements. But take a look what happens when we get down actually to krypton and xenon, and even argon. I mean, these three are relatively lower than helium and neon. And you're going to see in the next chapter that actually, even though we talk about these being stable, there are actually compounds that have xenon that have been found in nature, and some with krypton. I know that we've made them in the lab with argon, but I don't think there's any compounds that have been made with neon or helium. But these can actually chemically react because their ionization energies do actually dip down because of the fact that they have such large numbers of energy levels, so those electrons get easier and easier to pull away. Alright, so let's recap here. We looked at a couple of trends. You might want to draw this on your chart or on your periodic table. We're going to do this in class if you missed this, but that's okay. We're not going to do electron affinity, so you can ignore that one. That one's not important. Really, the ones you're looking at, atomic radius and here. So the atomic radius gets bigger as we go over here. Ionization energy increases in this direction. So we can see they're opposite each other. So as the atom gets smaller and smaller, it's harder to remove that electron. As the atom gets bigger and bigger, that's why it's easier to remove. And that's why metals lose electrons and nonmetals gain electrons. Also notice that there's metallic and non-metallic character. I'm not going to hold you to that right now, but we'll talk a little bit about that in class. But the idea is that there are other trends that are on the periodic table that we're going to look at, and we're going to keep adding to this. All right, guys, we'll finish this up in class, and I'll take your questions later. Thanks a lot.